This course is about using the warming rays of the sun to heat your home, while saving energy cost and reducing your impact on the planet. Solar heat is a free source of energy. This course will show you how to capture, distribute, store, and conserve heat for your home here in Maritime Canada. In the following module, we will explore aspects of the sun and solar radiation that creates our regional climate and how it affects the climate in your home.
This home is one of over 90 homes that I have designed and built since 1976. I am grateful to all of those that have been involved. We hope that you will find these videos useful in your solar endeavor. My name is Don Roscoe, Passive Solar Home Designer Builder. In the first section, we'll be looking at the Earth's spatial relationship with the sun and how it influences the amount of solar energy that arrives on the surface of the Earth. We orbit the sun every 365 days. At times, that orbit is circular, and at other times it's elliptical. And this causes us to be closer at times and then further away at other times.
Our Earth spins on its axis every 24 hours. This gives us our day when we are facing the sun and night when we are facing away from it. Also, the Earth's spin axis is slightly off of perpendicular with the plane of the Earth's orbit by about 23.5 degrees. This tilt changes the length of our days and nights, which creates our seasons. We can see in this diagram that we are tilted towards the sun in the summer, away from the sun in the winter, and in the spring and fall, we are halfway in between, giving us equal day and night. We call this the equinox. All of this determines our relationship with the sun and creates our climate. Here in the Maritimes, we are situated about 45 degrees north latitude, which is halfway between the equator and the North Pole. Unlike the tropics, our seasonal climates are much more variable. In the Maritimes, the sun rises and sets at very different times and places, depending on the time of year. In this diagram, you can see the arc of the sun in the winter, with it rising late in the morning, staying low in the sky, and setting early in the afternoon. This gives us a short day with a few hours of daylight. At the equinoxes, fall and spring, the sun rises above the horizon at 6 a.m. and sets below the horizon 6 p.m. solar time. This gives us 12 hours of sunlight and 12 hours without it. And finally, the summer sun rises much earlier in the morning and climbs much higher in the sky. It sets later in the day, giving us more hours of sunlight. As a result, our solar resources are much greater in the summer than in the winter.
So the challenge for passive solar design is not one of capturing the short winter sun. It's of not capturing the longer, stronger summer sun. With climate change bringing increasingly hotter summers, you not only need to design your home for the microclimate on your site as it is now, you need to design it for what it will be 20 years from now. The home you build today is a legacy you leave to future generations.
We will now follow the sun's radiation on its journey through space and our atmosphere, through to the surface of our planet. The sun radiates a broad electromagnetic spectrum through the vacuum of space. As it approaches Earth, it will first encounter the Earth's magnetic field. This field deflects most of the high-energy, short-wavelength spectrum, X-rays, and gamma radiation. By deflecting this high-intensity radiation around and away from Earth, life can flourish on the surface of the planet. At 45 kilometers above Earth's surface, the remaining radiation encounters the stratosphere, which contains ozone. Ozone neutralizes some of the more intense ultraviolet radiation, again protecting life. At 12 kilometers above Earth, the sun's radiation enters our atmosphere, or troposphere, which is our weather zone. The weather zone consists of 78% nitrogen, 21% oxygen, and 1% mostly argon, along with minor amounts of carbon dioxide, carbon monoxide, and other trace gases. Of course, we also need to account for the various forms of water vapor.
A lot will be happening in the very thin shell of the troposphere. We will next look at some of that activity as we follow the sun's radiation down to the surface of the Earth.
On a clear day, the remaining short-wavelength spectrum, the low-intensity ultraviolet, through the visible and infrared radiation, reaches the surface of the Earth. The surface warms and re-radiates in the infrared back to space. Our atmosphere also contains water vapor in the form of clouds, rain, snow, and hail. High, thin clouds will allow most of the spectrum to reach the Earth's surface. That surface then reflects and re-radiates the absorbed infrared radiation up to the clouds, where it is trapped and re-radiated back down to Earth. This has an overall warming effect. As the clouds get heavier, less of the sun's radiation passes through to the Earth's surface. Low, heavy clouds reflect most of the incoming radiation back into space. They also trap and reflect back infrared radiation coming up from the Earth's surface. This has an overall cooling effect. On balance, clouds have a cooling effect on the Earth's atmosphere. On a clear day, the sun's short-wavelength high-energy radiation reaches the surface of the Earth. It will be either reflected or absorbed and then partially re-emitted as long wavelength, low energy infrared radiation back out through the atmosphere. This depends on the nature of that surface. For example, the dull, dark surfaces of highly conductive materials, such as asphalt paving, will absorb most of the radiation and re-radiate a small portion of it back through the atmosphere. Ground vegetation, forests, and oceans also absorb heat and re-radiate it in the same way. On the other hand, shiny bright surfaces, such as that of snow or ice, will reflect most infrared radiation as low energy, long wave radiation back through our atmosphere. Over the entire Earth's surface, about 30% of incoming radiation is reflected back to space. While clear air is mostly transparent to incoming short wavelength radiation, a significant amount of the outgoing long wavelength infrared radiation is absorbed by trace gases in the atmosphere. This heats the air, causing it to radiate in all directions, out into space and back towards Earth. This further warms the Earth's surface, creating what we call the atmospheric greenhouse effect. The ratio of how much energy radiates into space and how much radiates back to Earth depends on the amount of trace gases in the atmosphere. The less and fewer kinds of trace gases there are, the cooler the planet. The more trace gases, the hotter it will be. The increasing amount of carbon dioxide and monoxide and other trace gases in the atmosphere increases this warming effect, causing climate change. We currently face an increasingly warmer climate, with more severe temperature, wind, drought, and other atmospheric effects.
Next, we'll be looking at a similar greenhouse effect that creates the climate inside your home. On a sunny day, you can get diffused and direct sunlight. But you also have to account for the sun reflecting off of snow, ice, water, glass walls, and other reflective surfaces. You need to account for all of these in the design of your passive solar home.
As we saw before, the sun's path across the sky is constantly changing with the day and with the seasons. Successfully capturing the sun depends on your window's orientation, how they face the sun's journey across the sky. Ideally, you will maximize solar gain in the winter and minimize solar gain in the summer. So let us look at how orientation affects the duration, time of day, and intensity of the sun's radiation striking the glazing surface, and how this relates to getting the right orientation for your passive solar home. The more you face north, the less you are going to see the sun. This should generally be avoided. Facing due north, your glazing will see the sun near the horizon for only a brief period of time and only over a few weeks at the summer solstice. You will not be getting appreciable solar gain, and you will never see the sun during the rest of the year. If you do have northerly views, follow along closely to the Design Resolutions section for suggestions. The further you orient away from north, the more sun you will see. Facing east during the summer, your glazing will see the sun rise early in the morning until high noon. In the winter, your east-facing glazing will see a later rising sun for a much briefer exposure. Facing south, your glazing will see the winter sun the whole time it is above the horizon. So if you want to maximize your solar gain, this is the general direction to face. Facing south during the summer, you will see the sun from about 6 a.m. to 6 p.m. solar time. Facing west, your glazing will see the sun from high noon to sunset. Because the sun sets later, your glazing will see the summer sun longer than in the winter. So, facing due south gives you the longest duration year-round and gives you the best potential for solar gain. That is, if there is no obstacles blocking the sun. This is one of the fundamentals of passive solar design in our climate. Facing due south is ideal, and this is where you will want to face most of your glazing. Facing away from south will affect your winter and summer gain, and also the time of day that you will get that gain. Since the Earth rotates 15 degrees in 1 hour, we will use this as our increment as we look at what happens as we face away from south. For winter heating, we want our glazing to offer a net energy gain. That is, we want to gain more heat energy when the sun is out than we lose when it is not. So, if we face off of south 1 hour or 15 degrees, we lose 5% of what we could have gained if we faced due south. Moving off by 2 hours, or 30 degrees, we lose 15%. By 3 hours, or 45 degrees, we lose 35%. We have now lost 1/3 of our potential gain. At some point, we will lose more heat than we gain. That point is determined by the ratio of how much heat we gain versus how much we lose. How much we lose depends on our window's ability to prevent heat loss, or their insulation value. In our climate, building codes require double glazed windows with low emitting, that's low E, coating, and argon gas. With this window type, your break-even point is about 45 degrees off of south in either direction. Going further off of south, it is a good idea to increase your window's insulation value by using triple glazing, double low E coating, and double argon. This is especially important for windows that face northward.
We have already seen that facing south maximizes the time of your exposure to the sun. But sometimes you have a view that's not to the south. So we now need to look at the time of day of that exposure so we can determine the length of your solar gain.
Facing southeast in midwinter, the sun will be just above the horizon, while in the summer, it will be higher in the sky at that same hour. In both cases, summer and winter, you will be getting the most intense radiation at mid-morning. In winter, you will take that gain anytime you can get it. In the summer, that gain comes at the coolest time of the day, causing moderate overheating. If you are facing southwest, in the winter, you will see the setting sun with little heat gain. However, in the summer, you will be facing the sun with your maximum gain at the hottest time of the day. You need to avoid southwest to west-facing glazing because of this significant summer overheating. If you have views in that direction, go to Design Resolutions for suggestions. The intensity of the sun's radiant energy depends on how squarely it strikes the surface of the glass. Notice that with the sun's radiation striking the glass squarely, there is little reflection. The more you vary from this, the more the radiation will be reflected and the lower the intensity. How solar radiation strikes the glazing determines how much will get reflected and how much will pass into the glazing. With a gloss surface, as the angle gets greater, reflectance increases. However, if you have a membrane with a matte surface, more energy will be absorbed into the glazing and less will be reflected. The light that enters will be diffused and less intense. This is easier on plants and people, but it will obscure your view to the outside. This is a great option for a greenhouse. The omnidirectional light prevents plants from growing towards the sun. In this sectional view, notice that when the low sun's radiation directly strikes the glazing surface, it is concentrated over a small area, making it intense, while in the summer, that same radiation striking the surface from a high angle spreads the radiation over a larger area, making it less intense. This plan view shows how this principle applies to the sun's radiation striking the glazing surface at various angles. The more oblique the angle, the less the intensity at the glazing surface, and the more that will be reflected. So, when we are facing south, we are capturing the summer sun at its highest point in the sky, thus reducing the intensity of that gain and our overheating. It also reduces how far the sun penetrates into the building. In the winter, we will be capturing the sun when it is much lower in the sky at a higher intensity, increasing our solar gain just when we need it. It also increases how far the sun penetrates into the building. Facing due south is ideal. It maximizes winter gain and it minimizes summer gain. Not only do we need to consider the sun cycle, we need to account for the temperature cycle. The shortest day of the year is around December 21st. But when is it coldest? It is 6 to 8 weeks later in the middle of February. By that time, the day is longer, the sun is higher in the sky, and the colder air holds less water vapor, creating fewer clouds. As a result, our solar gain will be slightly less intense, but over a much longer duration. Overall, this is beneficial. The longest day of the year is around June 21st. But when is it hottest? It is later in the middle of August. At that time, the lower afternoon summer sun's radiation more directly strikes the vertical southwest to west-facing glass. You are now getting your maximum gain not only at the hottest time of the day, but also at the hottest time of the year. You are really going to cook. You need to avoid southwest to west-facing glass.
Our initial projects were passive solar greenhouses, and most of them have sloped glazing. And just like with vertical glazing, we want to optimize our winter gain without cooking ourselves in the summer. Any sloped glazing is going to increase the duration of exposure to the sun and its intensity.
Notice in this image that the rising morning sun will only see south-facing vertical glass after it passes through east. In contrast, it will see sloping glass much earlier. The setting afternoon sun will not see vertical glass after it passes through west, while it will see sloping glass. Sloping the glass increases the amount of time, the duration that the sun strikes the glass. The flatter the slope, the longer the summer sun will strike the glass directly with greater intensity. As we saw earlier, sloped glass is less likely to receive reflected radiation than vertical glass. Facing south with a large area of glass sloping beyond 22 degrees will create real late summer overheating problems. Facing southwest to west will make it even worse. And again, you need to factor in the temperature cycle and our warming climate.
So far, we have considered the sun's radiation directly striking the glass. But sometimes the sun's radiation is going to reflect off of shiny and white-colored surfaces.
In nature, this would be mostly from surfaces such as water, ice, and snow. But adjacent buildings can also reflect radiation under the right conditions. The lower the sun is in the sky, the more likely the reflected radiation will directly strike your vertical glazing. With winter's lower sun, you will be increasing your solar gain just when you need it. But let's look at a couple of waterfront examples in the summer. Facing east, with the summer sun being lower in the sky in the morning, we will be getting the reflected gain at the coolest time of the day. Okay. At noontime, the sun will be higher and the solar radiation will be reflected back into space. Okay. But if your house faces southwest to west, in the late afternoon, you will be getting your solar gain from the lower sun at the hottest time of the day, and you're going to overheat. Not okay. You need to be aware of how and when the sun will reflect off the water surfaces onto your site. Also, be aware that the reflective surfaces of patios, decks, or pools adjacent to the building can also reflect the sun, contributing to further summer overheating. Or additional winter gain, especially when there is snow on the ground. If you need to intercept the sun's radiation, do it before it strikes the glazing. If you don't, the glass in your sealed window unit will capture a portion of the radiation on the way through, warming it up. With multiple glazings in sealed window units and thicker glass in larger windows, more heat will be captured, the hotter the glazing will get, and the more susceptible your windows will be to seal failure. Shading from the sun on the inside usually involves reflecting a good proportion of the remaining income radiation back out through the glazing, further heating it and making matters worse. You really do not want to do this. So how do you intercept the radiation before it becomes a problem? Horizontal overhangs can be effective at shading the high summer sun while allowing the lower winter sun through. This works for south-facing glazing, but we have to account for the temperature cycle. That is, the lower summer sun at the hottest time of the year in August. Horizontal overhangs do not work for shading reflected radiation. And as we saw, they can add to reflected radiation. Also notice how the overhang affects how much further the lower sun penetrates into the home compared to the higher sun, and how this enhanced exposure increases your floor's ability to absorb the winter sun's radiation. If your glazing is facing southwest to west, you will have to extend the overhang even further. Here, a retracting canopy will allow you to adapt to the sun and the weather. A fixed slatted canopy can be designed to allow more of the low winter sun and less of the higher summer sun. At its lowest point, the winter sun will be at a 1/2 or 26-degree angle. At its highest point, the summer sun will be at a 2/1 or 64-degree angle. These are at their extremes. You will want to be somewhere in between, as you do not want to sacrifice your precious winter gain. You can also create a natural overhead canopy of vines and other growth that shed their leaves with the seasons. This can protect you from the summer sun while allowing much of your winter gain to pass through. Planting or saving deciduous trees that grow beyond 45 degrees southwest can be used for afternoon shading in the summer without sacrificing significant winter gain. The lower branches can be trimmed to preserve the views.
We will now follow the sun's radiation as it passes through the glass into your home on a sunny day, and how it passes back out through your glass on a cold winter's night. We will now look at the various types of glazing.
Ultra clear glass, acrylics, polycarbonates do not capture much of the sun's radiation. allowing most of the sun's visible and infrared radiation to pass through. On a cold winter's night, they will also allow most of your home's infrared radiation to pass back out, affording little insulation. Textured glazings and semi-transparent membranes will diffuse a shaft of light, softening and spreading the light in more directions onto more surfaces. You will also get less intense light striking your interior surfaces. This can prevent radiation deterioration on susceptible surfaces, such as fabrics and items prone to fading. It also is the preferred light for most plants and for most human activities, but it will obscure your view out the window. Standard window glass has impurities in it. This is a block of window glass from the manufacturer's kiln. Notice how green it is. This is because the impurities in the glass capture a portion of the sun's radiation as it passes through, while reflecting a green hue. In this picture, notice how the light from the ultra-clear glass below the crossbeam reflects off the gray stucco inside and the blue sky outside. Now look above the crossbeam and see how the regular glass has greened both the gray stucco and the blue sky. The thicker glass from larger windows and multiple glazings typical in a passive solar home will increase this greening effect. This will affect your perception of the color of your decor inside and what you see outside. We will talk about color in the next section.
Your window is the interface of the sun's energy flowing into your home when the sun is out and flowing back out when it's not there.
Some light will be reflected when it strikes the glass. The more oblique the angle, the less intense it will be, and the more that will be reflected. What is not reflected will radiate through the glazing. This depends on its clarity and thickness. The less clarity and the thicker the glass, the more the radiation will be absorbed by the glazing, causing it to heat up. The absorbed heat energy will disperse within the glazing. We call this conduction. The air on the inside face of the glazing absorbs heat energy from the glazing, gets warmer, expands, and gets lighter and rises. We call this convection. In double glazing, radiation passes through to a second layer of glazing, and the whole process is repeated, with more radiation being absorbed and less passing through into the room. Similarly, with triple glazing, the process is repeated yet again, with a further reduction in the radiation passing through into the home. After passing through the glazing, we now have the remaining sun's radiation striking the surfaces inside your home. This will include, in decreasing energy, low energy ultraviolet through the visible into the infrared spectra. The light will appear green. In fact, this is a reflected light. The higher summer sun will strike the floor more directly than in winter, but will not penetrate as far into the space. The lower winter sun will strike more of the floor area at a more oblique angle, thus less directly. The more directly the radiation strikes the surface, the more intense it will be. The smoother and shinier the surface, the more that will be reflected, and the less that will be absorbed. Conversely, the more dull and textured the surface, the greater the surface area that is struck by the radiation. Thus, more will be absorbed and less reflected. What we see is our visible spectra. When we see the color white, we are seeing most of the visible color spectra being reflected. When we see a particular color, it is that reflected color, or the combination of colors, radiating to our eyes, while the remaining spectra has been absorbed. Here, we see the color red. Here, we see the color yellow. Here, we see the color blue. When you see black, and in particular a black matte surface, all of the visible color spectrum is being absorbed. It is, in fact, what we don't see because it's all being absorbed. For maximum radiation absorption, this is the color and the surface type you will want to use. A darker colored, matte finished tile will absorb much more radiation than a lighter colored, glossy tile. So will other darker surfaces inside your home. What we don't see is the lower energy, longer wavelength infrared radiation. It functions in the same way as visible light. All radiation that strikes a cooler surface will be reflected or absorbed, transferring energy to that material and warming the surface. If the surface material, like glass, is a good conductor of heat, it will absorb most of the heat energy into itself while re-radiating less. Dense materials such as concrete, masonry, and tile also do this well, and thus have good thermal mass storage capacity. We will look at this later. If the surface material is a poor conductor of heat, it will absorb less of the radiation and re-radiate more. Less dense materials, such as wood and carpeting, are poor conductors, more useful as an insulating material. The hotter surface temperature will radiate and conduct more energy into the air, warming it. Warming air expands, gets lighter, and rises. At the same time, we have warming air convecting up off the surface of the warm radiated glass. The taller the glazing, the longer and stronger this upward flow will be. These two processes create an accumulation of the hotter air stratifying on the ceiling.
We have seen what happens when the sun's radiation passes through the glazing into your home. In the summer, if you have a large amount of glazing, you run the risk of summer overheating. The amount of glass plays a major role in determining the climate inside your home. Next, we will look at how we can cool this situation down.
In the winter, given that any new home must be well insulated and relatively airtight, that same large area of glazing is going to be a main source of your heat loss. This will create underheating. When there is no winter sun, the coldest surface is going to be the glazing in your window. Warmer inside surfaces facing that glazing will now re-radiate as long wavelength infrared to and through that cold glazing surface. This depends on how directly they face, how close they are, and how large the temperature difference is at the glazing. The infrared radiation passes out through the glazing, which will absorb a portion of the radiation, slightly warming the glass. The still cool glazing will absorb heat from the air at its surface. This will cause the air to contract, get dense, and convect downward. The taller the glazing, the longer this process will last, and the colder and stronger the downflow across the floor will be. If the floor is a good conductor, the cool down flow will absorb heat from the floor, expand, rise, and dissipate as it flows into the room. If the floor is an insulator, less heat will be absorbed, and the cool down flow will move further into the room. Interior wall surfaces may further warm this air, causing it to rise. We now have stratification of hot air on the ceiling and cold air on the floor. We need to redistribute this. While the glass is your main source of solar gain, it is also the major source of heat loss. It has the lowest insulation value of any exterior component in your home. So let's revisit the energy as it flows out through the glazing. The energy absorbed on the inside surface of the glass will conduct through to the cooler outer surface. Here, two things happen. First, air at the surface will absorb energy, expand, and convect upward. To impede this upward flow, we keep the airspace narrow, less than 1/2 inch. Second, infrared energy will radiate across the airspace to the cooler outer pane of glass. To prevent this, we add a low emissivity coating that blocks this outward flow. This reduces this outward heat radiation by about half. This coating also allows the visible and ultraviolet radiation from the sun to pass through into your home. Still, some energy will radiate and convect across the airspace to the inside face of the outer layer of glass. This will absorb heat from the airspace at its surface, causing the air to cool, get dense, and convect downward. We now have a convection loop, like a conveyor belt, transferring energy across the airspace. The taller the airspace, the faster it will convect. To slow this, we replace the air with a heavier inert gas called argon. In an average 4-foot window or taller, this will reduce your heat loss by about 10%. Low E and argon are the standard building code requirements in our region. Finally, the remaining heat will pass to the outside of the exterior glazing, where it will radiate, conduct, and convect into the cold atmosphere. If you want to further reduce your heat loss by half again, you can add another middle glass layer with low emissivity coating along with another argon-filled airspace. This will give you triple glazing, which is recommended for north-facing windows. We have now seen the sun's radiation pass through space, through our atmosphere, through our glazing, into and out of our home. We will now return to look at the climates that this has created inside your home. As we saw earlier, warming air rises while cooling air falls, resulting in a stratification of temperature. If there is an overall heating condition, such as when the sun is radiating into the room, you will get a concentration of heat on the ceiling. If it is a horizontal ceiling, that heat will be evenly distributed over the ceiling area. If it is a sloped ceiling, it will be concentrated at the peak. The steeper the slope, the more concentrated it will be, and the higher the temperature stratification. When there is a cooling condition, such as when there is no sun, you will get a concentration of cooler air on the floor. Again, temperature stratification. Adding more glazing area increases both heating and cooling, and heat stratification. Any passive solar gain that is not absorbed by the surfaces in your home will end up as hot air on the ceiling. The hotter that air is, the greater the rate of heat flow through the roof insulation to the cold sky, and thus the need for higher insulation levels in your roof compared to your walls, which do not face the sky. We need to actively cycle the air to redistribute the heat. We have passively captured the sun's energy that radiated through your windows. We have seen how some of this energy is absorbed on the way into your home, and how those warm surfaces will warm the air, causing it to rise to the ceiling. When it is cold and there is no sun, heat from the inside air will pass out through those windows, cooling the air and causing it to flow down to the floor. We now have temperature stratification, with hot air on the ceiling and cold air on the floor. With temperature stratification comes humidity stratification. Hotter air has a higher vapor capacity than colder air, so most of the water vapor will be stratified on the ceiling. You do not see it there. You only notice it when that moisture-laden air cools, then falls with the moisture condensing on a cold surface, just like at the bottom of a window. We need to redistribute this moisture more evenly within the air mass. With better insulated and airtight homes, there are few passive ways of destratifying this air. This does not work for your comfort, your health, or for storing the heat. Based on research and experimentation, our building codes now require controlled ventilation in and out of your home, and air in and out of every living space. We have to actively cycle the air.
We breathe in and out 12 to 18 times a minute. That's 5 to 8 liters of air in and out of your lungs every minute. Guess who's filtering the air? You need to filter the air in your home faster than you filter it through your lungs. It's all about the rate of filtration. We need to actively cycle the air through the filter.
Membrane filters work by passing air through a fine membrane. The finer the membrane, the more it interfaces with the air, slowing its passage through the membrane. The accumulated particulate matter requires that the filter be replaced periodically. Instead, for over 30 years, we have been using a non-membrane electronic electrostatic air filter. They ionize particulate matter in the air, giving them an electrostatic charge. The charged particles then pass through oppositely charged metal fins that attach these particles to their surfaces. They allow free airflow, are permanent, cleanable, and use little electricity. If you have a lot of glass, you're going to have to go beyond the building code's airflow requirements. Air has a low heat capacity. You need to move a lot of air to move a lot of heat. As a rule of thumb, our experience has shown that moving the whole air mass in a room or the home in about 30 to 40 minutes does the job. Variable speed, high-efficiency electronically commutated fan motors can do this quietly and at low cost, while allowing you to adjust it to just the right airflow rate. Leaving the hot air on the ceiling in the winter will cost you more in heat loss than it takes to run this fan. The continuous gentle airflow is also welcome during the hot summer. To maximize airflow and destratify the air, we need to place the air registers accordingly. To pull the hotter and more humid air off the ceiling, place the return registers high on the wall, near the ceiling, away from vertical and horizontal corners, and towards the middle of the interior wall. To intercept the cold air flowing down from windows and exterior walls, place floor registers under them, about 6 inches off of the wall. This will throw a curtain of upward flowing air to intercept the cold down flowing air. Most of this high flowing air is happening at the perimeter of your space, leaving the interior with a gentle airflow. Ceiling fans will destratify the air, but you may find yourself under its high flowing air in the middle of the room. This will cool you in the summer, but you do not want this in the winter. Moving and recycling the air allows you to transfer heat into and out of storage and to destratify heat and humidity. It will also filter the incoming air and the air in the home. This will create a more comfortable, healthier interior environment.
We have completed the sun's energy journey through space, through our atmosphere, and through our glazing into our home.
Inside, it will strike the surfaces facing it. What is not reflected will be absorbed at the surfaces of cooler, solid materials. If that material consists of densely packed atoms, the radiant energy at the surface will readily conduct into and within itself. Materials such as masonry, concrete, stone, and ceramic tile will do this. If the materials are less densely packed or open-celled, they will not so readily conduct within themselves. Materials such as carpeting, wood, and cork flooring are of low density, and we call them insulators. We use them to slow the movement of heat. White and light-colored surfaces will reflect more energy, while darker surfaces will absorb more. Matte and textured surfaces will further increase absorption. Matte black finishes give you the highest energy absorption. With the sun's radiation being absorbed, there will be a temperature gradient as the heat conducts through the material, hotter at the surface and diminishing further from the surface. The stronger and the longer the radiation, the quicker and further the heat will penetrate into the material. Only the top inch or so will be effective thermal storage. A similar process can happen with walls. That is, if the walls are made with plastered lath. But most walls are built with drywall sheathing, a gypsum material that is surfaced with paper. Paper is an insulator. Think about holding that paper cup full of hot coffee. This limits the ability of the sun's radiation to readily conduct into the gypsum to be stored. However, if you use cement board instead, you will now be storing heat. When the sun's radiation stops, the surface is cool and the process reverses. That surface will now begin to radiate heat to near-facing surfaces that are colder. Also, the cooler air at the surface will absorb heat and convect it away. If you are standing on that cold floor material, heat will conduct from your bare feet into the floor. If you are near a cold wall or window, you will be radiating heat to those surfaces regardless of the air temperature. Air is also transparent to radiant heat, and it has a low energy density. Earlier, we looked at redistributing this hot air. We will now look at how to actively store that heat.
In our experiments with greenhouses, we learned that they massively overheated and underheated because of all that glazing. So we evolved methods to distribute and store that heat, which moderated those extremes. We learned that you have to move a lot of air to move a lot of heat, and you have to expose that hot air to as much heat-absorbing surface as you can.
The best heat storage material that exists in most buildings is the concrete in your foundation. By insulating concrete foundation walls on the outside and finishing the inside with a stucco finish, we allow the interior heat to migrate into this concrete, thus storing it. By pouring a concrete slab foundation floor that is fully insulated and vapor sealed underneath, we are able to embed air ducts in that slab that fan out to the exterior. By recirculating air through these ducts, we are able to activate a lot of this concrete. So we now have taken the hot air off the ceiling and transferred that heat into the concrete slab that you are standing on. The slab will now hold heat for days, leveling out your day and nighttime temperature extremes, thus preventing over and under heating. We also learned how to use ground insulation techniques to replace frost walls. This simplifies construction and allows us to use that concrete to thicken the slab. All of this can be done at the same cost as a conventional foundation with the same amount of concrete, and be done in one pour instead of two. We have created the Passive Solar Construction course for designers and builders. It will take you through the design theory and the construction details and methods. You have already seen why we need south-facing glazing to optimize the winter solar gain and minimize the summer sun. The following designs will show various ways of resolving issues of non-south orientations, views, and slopes. To begin, you will want to use southerly spaces such as dining and living areas that are transparent. They can share the sun and the views with other spaces. So first, let us look at south-facing glazing when the view is not south. Most windows are centered on their walls. This works for solar gain if the glazing and the views are both facing south within 15 degrees. But also, we will want to avoid southwest to west-facing glazing to prevent solar summer day overheating. So what can we do when the view is to the southwest? If we move the centered window to the west corner, we will see more of the southwest view at an angle without losing the southern orientation. Adding a smaller west-facing window, we will now see even further to the western view with only modest afternoon overheating. Duplicating and staggering this arrangement will allow you to see through adjacent transparent rooms to the south through to the west with minimal summer overheating. With views to the south, through west, to northwest, we will have to take a different approach. Adding a screened-in west-facing porch will shade the home from the late summer afternoon sun. This minimizes overheating while giving you views from the southwest through to the northwest. Covering the porch screening with plastic will provide a winter thermal buffer and a handy place for winter firewood. A southwest step-down greenhouse will create an intermediate transparent space with views from south through west. In the summer, you can ventilate its heat separate from the home. In the winter, you can tie the greenhouse into the home air recirculating system, thus providing its solar gain and moisture to the home. Remember, winter air holds very little moisture. All of these approaches can work for east views by flipping the diagrams. Here we are less concerned with summer overheating because it happens in the cooler morning temperatures. With northern views, you will have transparent spaces separating the south-facing glazing through to the north-facing glazing, as shown here. Notice the multitude of views from various locations in this plan. You will want to minimize the height and width of the north-facing glazing without losing your views. Also, you can minimize the exterior exposed northern wall area from the cold winter winds by lowering the wall heights and by earth berming below the windows, as shown. Modest northerly slopes may allow you to access the low winter sun by allowing it to pass through an opening in the upper floor to the lower floor. You can also capture it through upper clear-story glazings. This can bring sunlight into the northern spaces. The heat gained from this will rise and stratify high on the ceiling. This will require a recirculating fan to redistribute this heat and store it in the slab. Few home sites are ideal. We hope you will find these examples useful in designing your passive solar home for your unique site.
This concludes Module 1, Solar Basics. As we have seen, the design of passive solar homes requires a different approach than what's used in conventional homes. The next 3 modules will cover site design, the planning of subdivisions, and solar construction.